Welcome to a screencast on an introduction to chemical bonding and Lewis structures. The objectives of this screencast are to describe covalent and ionic bonds and their formation, and to draw Lewis electron dot structures for simple molecules, ions, and ionic compounds. And let's start by considering a very important generalization, one we've actually seen before, which is that the noble gases have an electron arrangement or an electron configuration that is very stable. This is why they're not reactive, not very reactive. They have a stable electron arrangement as they already exist. Now, it turns out that atoms essentially kind of like to end up with this sort of an arrangement, like a noble gas, which is normally 8 valence electrons. So we're a little bit anthropomorphizing atoms here, and we're saying that they like to end up with a noble gas arrangement. This might mean they gain some electrons, they might lose some electrons, or they might end up, as we'll see in a bit, sharing some electrons. But if they get a noble gas arrangement, they tend to be fairly stable. Now, we're going to look at this using some ideas proposed by the American chemist Gilbert Newton Lewis. Back in the early 1900s, he was looking into characteristics of atoms in terms of their electronic structure, and we use what are called Lewis electron dot symbols, so named after him, as a kind of simple way to describe chemical bonding and getting at structures of molecules and what's going on in bond formation and that sort of thing. And in Lewis electron dot symbols, we have the symbol of the element representing both the nucleus and the inner shell or core electrons, and then we use dots to represent the valence electrons. And here are a few examples of how this works. Let's start with the element magnesium. So it's an alkaline earth metal. It has 10 inner shell electrons, so we represent those inner shell electrons and the nucleus by the symbol Mg, and then it has 2 valence electrons, so we put 2 dots around it to represent those valence electrons. Aluminum, column 13, has 10 inner shell electrons and 3 outer shell or valence electrons, so Al with 3 dots around it. Phosphorus has 5 valence electrons, so 1, 2, 3, 4, 5 dots, and by convention we put the dots on the left, the right, the top, the bottom, and then once we have 4 dots, then we start pairing them up when we have the 5th dot or 6th or 7th, etc. And then one more, let's do bromine, which is a halogen. It has 7 valence electrons, so 1, 2, 3, 4, 5, 6, 7 dots, representing a bromine atom. Okay, so we can use Lewis symbols to represent atoms. We can also represent ions, and we can use them to represent ionic reactions. So let's do a simple example of that. Sodium in the Lewis dot structure representation has 1 valence electron, so 1 dot. It can react with the element chlorine, which has 7 valence electrons, or 7 dots. And notice, sodium has 1 dot more than a noble gas. Chlorine has 1 dot or 1 electron less than a noble gas. So if the electron from sodium in its outer shell is transferred to the chlorine, then sodium ends up with an electron configuration like a noble gas, and so does chlorine. And when that happens, sodium is, of course, a positively charged ion because it has 1 less electron. Chlorine becomes the chloride ion with 1 more electron and is therefore negatively charged. And then what we have is a positive ion and a negative ion that attract each other. And that attraction between positive and negative ion is what is called an ionic bond. Now, ionic compounds in general are held together by these kind of attractions between cations, positive ions, and anions, or negative ions. And these attractions are called ionic bonds, And as seen, for example, for sodium chloride formation, the elements sodium and chlorine can form sodium ion and chloride ion, which attract each other, and they actually make a big three-dimensional array where it's negative ion attracting positive ion, attracting negative ion, attracting positive ion, attracting negative ion in all directions. Now we can also use Lewis symbols to represent the formation of molecules. And an example of that would be the element fluorine, which has 7 valence electrons. It could bond with something in an ionic fashion. For example, it could bond with sodium, but it can also bond with another fluorine atom. And what ends up happening in this case is the 2 fluorine atoms, when they get close enough together, they can have their electron shells overlap. And in a simple way of looking at things, they have these 2 electrons shared between the 2 atoms. And those shared electrons, that pair of shared electrons, is what is called a covalent bond. So anytime we have a shared pair of electrons, we have a covalent bond between 2 atoms. And we often represent a covalent bond instead of by 2 dots to represent the electrons, but by a line between the 2 atoms. And so this line also represents a covalent bond. Now, one other thing to note, the covalent bond, these shared electrons, kind of glues the 2 atoms together, so the nuclei of the 2 fluorine atoms repel each other. But the electrons, being negative, attract both this positive ion or positive nucleus and this positive nucleus, and so they attract and hold these 2 atoms together. That's more or less what a covalent bond is. Now let's do a couple examples of molecule formation with covalent bonds and Lewis dot symbols. And let's start with carbon reacting with or bonding with hydrogen. Carbon has 4 valence electrons, so here are 4 dots. And notice each dot is kind of like half of a shared pair. So if this had 1 more electron, it would be sharing electrons and form a bond, and a hydrogen atom can do that. Well, same thing here, and there, and there. We have 4 different places where a hydrogen atom with 1 valence electron could come and share with a carbon. And each time we would have a shared pair of electrons, which would then be a covalent bond. And now let's write this in a little more compact form. When these 4 hydrogens combine to make CH4, methane. And we've got a shared pair of electrons, shared pair of electrons, shared pair of electrons, and a 4th shared pair of electrons. And if we look around the carbon, it now, counting all of the shared electrons, has 8 electrons around it. Stable electron arrangement like a noble gas. Hydrogen has 2 electrons around it. This is stable for the noble gas helium, and then same with the other hydrogens. So by sharing electrons, all of the atoms get stable electron arrangements and are, so to speak, happy about life. And we can also note each of those is a covalent bond. And we can, of course, write this in a somewhat more compact way as line, 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 each line representing a covalent bond between the central carbon and a hydrogen. Nitrogen can do a similar thing with hydrogen. Nitrogen has 5 valence electrons, which means 1, 2, 3 hydrogens can attach to it. That gives shared electrons in 3 different places, and we make the molecule NH3 or ammonia. And we can write this in the more compact form using a line to represent a shared pair of electrons or a bond, as indicated here, N bonded to H, bonded to a second H, bonded to a third H, and then there is a pair of electrons that are not involved in bonding, and those are what is known as a lone pair of electrons as opposed to a bond pair of electrons. And the last example we'll do is two oxygen atoms combining together to make the diatomic molecule O2. Oxygen has 6 valence electrons. A second oxygen also has 6 valence electrons. And if they share these two electrons, notice that we don't get an octet of electrons around the oxygen. Here we have 1, 2, 3, 4, 5, 6, 7. And similarly, 1, 2, 3, 4, 5, 6, 7. It's not quite enough, but if nature were to move this electron into the middle and this electron also into the middle, we would have 2 pairs of shared electrons in the middle. Notice it's the same number of electrons as before, and we have 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons around oxygen. Noble gas arrangement, same with the other oxygen. And lo and behold, we have formed not a single bond, but a double bond, 2 pairs of shared electrons. And this can happen as well. And how we write that in the more compact notation is 2 lines representing 2 covalent bonds rather than 1 line for 1 covalent bond. And that is almost it. Quick note on the unifying principle. In general, atoms gain or lose or share electrons in order to achieve a stable noble gas electron arrangement, and we often call this the octet rule because there are 8 electrons around each atom. And that is it for an introduction to chemical bonding and Lewis structures.